In this video, we're going to work some example problems related to the topic of calorimetry. So let's get started. Well, what is the difference between specific heat and heat capacity? What are the units for these two quantities? Which is the intensive property and which is the extensive property? So specific heat and heat capacity are both related to how the temperature of a solid, liquid, or gas body changes with respect to the amount of heat energy absorbed or released. Specific heat and heat capacity are pretty much the same thing, except specific heat is just per unit mass, whereas heat capacity is not per unit mass. So it's kind of like density. The density of something doesn't change based on the amount you have, right? If you've got 50 pounds of steel or 1 pound of steel, the density is still the same. And same idea. So like water, for example, the specific heat of water, no matter how much water you have, is the same. But the heat capacity of a glass of water versus a bathtub of water are different. The bathtub of water is going to have a higher heat capacity. So heat capacity is going to have units energy per temperature. So to give an example here, joules per Kelvin, let's say. So the idea is if you apply a certain number of joules of heat to some solid, liquid, or gas body, the temperature is going to change by a certain amount. And so you would put that change in temperature. If the temperature of a body changed by 50 Kelvin, it increased by 50 Kelvin, then that means this amount of joules of heat energy were added to it, right? You multiply 50 times the heat capacity. But specific heat is the same thing, but it's per mass. So something like, right? So if water in any scenario, the temperature increased by 50 Kelvin, then that means that the energy supplied to it was this many joules per gram of water. So then you'd have to also multiply by the number of grams of water. So a bathtub or a glass of water would be different, and to get the actual amount of joules or energy added to it. The intensive property is the specific heat because it doesn't depend on the amount of the substance, right? That's what intensive property means. And the heat capacity is the extensive property. It does depend on the amount, right? A bathtub of water is going to have a higher heat capacity than a glass of water, so it's an extensive property, but the glass of water and the bathtub of water are going to have the same specific heat. So that's an intensive property. It doesn't depend on the amount. Define calorimetry and describe two commonly used calorimeters. In a calorimetric measurement, why is it important that we know the heat capacity of the calorimeter? How is this value determined? So calorimetry is, the definition is, it's the measurement of heat changes. That's what calorimetry is. It's the systematic measurement of heat changes. Two commonly used calorimeters are the constant volume and the constant pressure calorimeter. And as the names imply, the constant volume is you're measuring heat changes in a constant volume environment, and a constant pressure calorimeter, you're measuring heat changes in a constant pressure environment. And so just to be clear, when we're talking about heat changes, we're saying if we think of the first law, this, literal heat changes, energy in the form of heat. That's what calorimetry is. But you can notice that for the two commonly used calorimeters, the constant volume calorimeter, as we know, the change in heat is equal to delta U because there's no PV work. And in a constant pressure calorimeter, the change in heat is equal to delta H, which is delta U plus the internal energy plus PV, right? The change in enthalpy incorporates the pressure volume work. In a calorimetric measurement, why is it important that we know the heat capacity of the calorimeter? Because if you have to know this in order to get the heat released or absorbed by the substance in question. Because what happens is, for the two most common calorimeters, so under a constant pressure or constant volume environment, you're trying to find the heat released by some substance or based on some chemical reaction. And to figure this out, what you're going to do is you're going to measure the change in temperature of something, right? We can measure changes in temperature. We have instruments that can measure temperature accurately. And the change in temperature that's being measured is the change in temperature of the calorimeter. So you need to know the heat absorption properties of the calorimeter. How much energy, heat energy, is transferred to or from the calorimeter for each change in degree temperature, or change in unit temperature. Because we can measure the change in temperature of the calorimeter, but we need to relate that change in temperature to heat energy. So you need to know the heat capacity of the calorimeter. If you know the heat capacity of the calorimeter, you can tie that change in temperature of the calorimeter to the heat energy that it absorbed or released, which you can then tie to the heat energy absorbed or released by the substance in question or the chemical reaction in question. And this value is determined by performing a reaction or burning a substance where that reaction or that substance, the heat content inside of it is already precisely known. So that way you know the heat that's going to be absorbed or released by the calorimeter because you know that property of the substance. So you can use the change in temperature and the known heat that's going to be released or absorbed to get the heat capacity of the calorimeter. Consider the following data, okay? When these two metals are placed in contact, which of the following will take place? Okay, so when you think about heat transfer, the process of heat transfer, heat flow, the only thing that the direction of heat flow is a function of is the temperature gradient. Now, the rate of heat flow, the intensity of heat flow, things like that, that depends on the material. But as far as the direction that heat is flowing, that is only a function of the temperature gradient. That's a property of nature. So the direction of heat flow is not a function of the type of material, the state of the material, so solid, liquid, or gas. A property of nature is that no matter what the circumstances, heat flows from higher temperature to lower temperature. And so that's all this question is asking about. It's like direction of heat flow. So we don't care about specific heats or mass. These come into play if you're talking about the rate of heat transfer, right? So if you have something that's more of an insulating material, then heat will flow more slowly through it. The only way heat flows from lower temperature to higher temperature is with some sort of an energy input involved. Like that's what a refrigerator is doing. There are no circumstances where heat naturally flows from a lower temperature to a higher temperature region. So here we're just going to look at the temperature gradient. The aluminum is at 40 degrees Celsius. The copper is at 60. So heat's flowing from the copper to the aluminum. That's it. Heat will flow from copper to aluminum because copper has larger mass. No. Heat will flow from copper to aluminum because copper is at the higher temperature. Yes. A piece of silver of mass 362 grams has a heat capacity of 85.7 joules per degree Celsius. What is the specific heat of silver? Okay, so it gives us the heat capacity, right? The measure of the amount of joules of heat energy absorbed or released per unit change in temperature, not with respect to the amount of substance. So it's the heat capacity of this amount of silver. But it wants to know the specific heat. What we know that specific heat is energy per unit mass per unit temperature. Here we've got energy per unit temperature. We want to get to energy per unit mass per unit temperature. So let's just divide this by this, right? So we get, right? So we'll get per degree Celsius and then, right, joules per gram degree Celsius. So let's just do this division. .237 joules per gram degree Celsius. Calculate the amount of heat liberated in kilojoules from 366 grams of mercury when it cools from 77 to 12 degrees Celsius. Okay, we need the specific heat of mercury. And you could think about, you'll be able to easily find a table in the chemistry textbook, or if you Google it, check your Google reference, make sure it's a good reference. You'll be able to find specific heats of substances, right? Because that's a material property. Heat capacity is not a material property. That heat capacity depends on the amount of substance. So if we look in the chemistry textbook, we see there's a table that lists some common specific heats. Mercury, 0.139 joules per gram degrees Celsius. Okay, so this is specific heat of mercury. All right, so we're going from 77 to 12. So 77 minus 12 is 65, but it's negative, right? The temperature decreases. T2 minus T1. Okay. Okay, what else? Now, how many grams are there? 366 grams. So now we're in joules. That's what we're looking for. Or wait, we need to get to kilojoules. So there are 1,000 joules for every 1 kilojoule. Now we're in kilojoules. That's what we're looking for. So we're not solving for the specific heat. We started with the specific heat. Minus 3.31 kilojoules. That's the amount of heat liberated. I mean, based on the question, we could remove the minus sign because it's 3.31 kilojoules of heat released, right? Not minus 3.31 kilojoules of heat released. You see what I mean? It's technically, yeah, if you're just saying, okay, based on the first law, like if we're saying, what is Q? Like, when you say heat liberated, you're implying the negative is already in there. But if you're just giving a technical answer based on the first law, then you put negative to say that the heat was released. To a sample of water at 23.4 degrees Celsius in a constant pressure calorimeter of negligible heat capacity is added a 12.1 gram piece of aluminum whose temperature is 81.7 degrees Celsius. If the final temperature of water is 29.4 degrees Celsius, calculate the mass of the water in the calorimeter. Okay, so they're saying negligible heat capacity. I think they're implying that styrofoam cup calorimeter. And so the way you can think about that is, for certain calorimeters, the reaction takes place. It takes place pretty quickly. And the idea is that the delta T you measure of the water, there's a negligible amount of heat that's being absorbed by the styrofoam cup, for example, at least in that time frame. Whereas for like the constant volume calorimeters that we studied in the textbook, you have to think about the surrounding water, but also the combustion chamber. All of that is part of the delta T that you observe. There's multiple parts that are absorbing heat. So in that case, you have to calibrate it, you could say, with a known substance, a substance with known heat content, get the delta T, and find the net heat capacity of the calorimeter. But here, for this specific constant pressure calorimeter, in some cases, you could just say the water is the only thing that's absorbing any significant amount of heat. So you don't have to calibrate it. You could just come to a table like this and get the heat capacity of H2O, or specific heat. I'm sure this is at atmospheric pressure or 1 atmosphere pressure, but you could get the specific heat of like water or whatever you're using in those environmental conditions. So here we've got the specific heat of H2O is okay. Well, and let's also get the aluminum heat capacity. So 0.90. Okay. So this aluminum is put into the water at this temperature. The aluminum is at this temperature. And it says the final temperature of the water is this. Calculate the mass of the water in the calorimeter. So with these types of problems, the key point to remember is that the heat transfers between the components are typically going to be the same. Either the components or multiple components, there's going to be some sort of way you can look at it to where the heat transfers from one component or components to another component or components are the same. In other words, all of the heat released by the aluminum is absorbed by the water, just the water. And it happens fast enough to where you don't have to consider the heat that was absorbed by the styrofoam cup or the calorimeter or the heat transfer to the environment. It's a fast enough process to where a large percentage of all of the heat is just being transferred between the aluminum and the water. So let's get the heat transferred from the aluminum. We've got 0.90 joules per gram degree Celsius. You have 12.1 grams of aluminum. Okay, and then now we need a delta T. So it goes from 81.7 to 24.9. So 81.7 minus 24.9, 56.8. This is negative. Okay. So you got 0.9 times minus 618.6. Okay, that's how much heat leaves the aluminum in this process. And I didn't specify this, but you might be asking, well, how did we know that the final temperature of the aluminum was 24.9? Because it doesn't tell us that, right? It says the final temperature of the water is 24.9. And that's something else you have to notice in these problems. The final state is also going to be in a state of thermal equilibrium, typically. For just a general heat transfer or calorimetry type problem like this, unless they clearly state otherwise, the idea is everything in the end, all the components, the calorimeter and the component you're studying, they come into thermal equilibrium. So if the final temperature of the water is 24.9, then that's going to be the final temperature of the aluminum as well. Okay, so, but again, we know that since this amount of heat left the aluminum, that's also the amount of heat that went into the water. So let's use the delta T of the water, because we know it's this minus this, or no, it goes from this temperature to this temperature, the delta T of the water, and the heat transferred to the water to get the mass of the water, and use the specific heat as well. So, okay, we know that there was 618.6 joules of heat transferred to the water. We could start there. All right. Now let's just bring in the specific heat here. So 4.184, it's joules per gram degrees Celsius. Okay. Now we just need to get rid of this degrees Celsius so we can get to grams. So what is the delta T? Well, it's 24.9 minus 23.4. It tells us the final and initial temperatures of the water. $1.5. All right, so now we're in grams. That's what we're looking for, grams of water. So okay, 98.6 grams of water. Okay, a quantity of 85 milliliters of 0.9 molarity HCl is mixed with 85 milliliters of 0.9 molarity KOH in a constant pressure calorimeter that has a heat capacity of 325 joules per degree Celsius. If the initial temperatures of both solutions are the same at 18.24 degrees Celsius, what is the final temperature of the mixed solution? The heat of neutralization is minus 56.2 kilojoules per mole. Assume the density and specific heat of the solutions are the same as those for the water. Okay, so this heat of neutralization, they're just talking about when you mix this acid and base, it neutralizes, right? And there's a heat associated strictly with that neutralization. And so the heat of neutralization, they're talking about an enthalpy, the heat of a reaction or whatnot. We're talking about enthalpy. We're thinking about when we see a term like this, heat of neutralization, we're thinking about a constant pressure process. Therefore, it's the change in enthalpy, but since it's constant pressure, it's also the heat transferred. The change in enthalpy, or the heat transferred in this constant pressure process due to the neutralization of the acid and the base, is this amount per mole. So this is for the chemical reaction. So let's write this reaction out, because this per mole is talking about it's per mole of reactant and product. So we need to get a balanced equation. All right, so HCl aqueous plus KOH aqueous. Okay, now it's a neutralization reaction, so let's put the salt. That would be KCl. Okay, let's check the solubility chart for KCl. And this is, but K is +1 and chlorine is -1. So this is the right, it's not like it's K2Cl or something like that. KCl. Okay, solubility. Compounds containing alkali metal ions are always soluble. So this is going to be aqueous and then H2O liquid. Okay, now let's balance this. So we've got 2 H's on the left, 2 H's on the right, 1 potassium on the left, 1 on the right, 1 oxygen on the left, 1 oxygen on the right, 1 Cl on the left, 1 Cl on the right. So this is balanced. And the delta H for this reaction, this is the heat of neutralization, because there's no, what they're saying here, the heat of neutralization, there's no chemical reaction going on here. There is, but that's what it's the neutralization that's taking place, right? This is the heat of this reaction. They're just calling it neutralization because that's what's taking place. The acid and the base are neutralizing. So this delta H is minus 56.2 kilojoules per mole. Okay, now what they're saying here is that the density and specific heat of the solutions are the same as those for water. So the density and specific heat at this stage, right, kind of like right when you add these two solutions before they start interacting, is going to be the same as this stage. And it's going to just be, we can assume it's whatever pure water is. Okay, so the specific heat of water is 4.184 joules per grams degrees Celsius. And then the density of water is 1 gram per cubic centimeter, which is 1 gram per milliliter. That's what a cubic centimeter and a milliliter are the same. Okay, so what we need to do is we need to find out how many moles are taking part in this reaction. And so we can see for every 1 mole of HCl consumed, 1 mole of KOH is consumed. And we're starting with the same volume and the same concentration. So we mix the same amount of moles of HCl and KOH, and based on the balanced reaction, it's 1 mole of HCl consumed and 1 mole of KOH consumed. So let's just we can use either one of these. How many moles of whatever are in a 0.9 molarity solution, 85 milliliters? Molarity is moles per liter, right? That's the units of molarity. So we've got in moles, and we know the volume, and we're going to do this in liters. 0.085 is equal to 0.90, right? Some amount of moles divided by 0.085 liters is equal to this in molarity. So I'm not going to put HCl or KOH. .0765. Okay, now from here we can use this to determine the heat transfer, or the delta H, same thing here. using this value. And the way you interpret this is this many kilojoules per 1 mole of HCl, or per 1 mole of KOH, or per 1 mole of KCl. This value corresponds to this specific balanced equation here. When this specific balanced equation takes place, 1 mole of this reacts with 1 mole of this to produce 1 mole of this and 1 mole of this. This is given off. So what we need to do is multiply this times 0.0765. If this was just 1, if we started with 1 mole of HCl, we just multiply by 1. But now we're going to multiply by 0.0765. So the delta H is equal to 56.2 times this, 4.30. Okay? So this is the amount of heat given off as a result of this reaction here. You mix these two solutions together, and as a result of this neutralization of acid and base, this amount of heat is given off from the reaction into the calorimeter. Okay, now this is a little confusing because it's not like they didn't tell us like some of the other problems that the calorimeter is, we could just assume is just the water, the surrounding water. We have to consider the calorimeter as well as absorbing heat. So the idea is this heat, right? This heat here, this was given off, okay? This was released and absorbed by what? This was released, let's put 4,300 because we've got these heat capacities in joules. 4,300 joules of heat was released and absorbed by the surrounding or the solution. We're not going to say water, we'll say the solution, which we're going to assume acts like water, and the calorimeter, right? Okay, so let's write this out. 4,300 is equal to, what's Q solution? It's the heat capacity of the solution, which we're going to just treat as water. So the heat capacity of water times the delta T of the water. Now, to get the heat capacity, we have to go use the specific heat, so we need the amount of grams of water here. And to get that, we know that we mix, we're going to use the fact that we mix this amount of these two amounts of solution. So 170 milliliters of solution. So 1 times 170 means you have 170 grams of solution. So 170 grams times the specific heat of water times, right? So we've multiplied by grams. We multiply this. We're in, let's get our units right. We're in joules here. So these joules match. We have 170 grams, right? This 1 times 85 plus 85, so 1 times 170, so we're in grams. This amount of grams. So grams times joules per gram degrees Celsius. The grams cancel. Now we have joules per degree Celsius. Now we just need to multiply times the delta T, which would be in degrees Celsius. So let's say temperature final minus the initial temperature. Do we have the initial temperature? Yes, 18.24. Okay. Now, the calorimeter, Q calorimeter, the heat capacity times the delta T. Well, they give us the heat capacity here, so we don't have to multiply times some amount. So this is just, the components of the calorimeter. We don't know anything about the calorimeter, but they just give us this. They determine that in their own. So 325, we don't need to multiply by grams, just another degrees Celsius term. That's the delta T. So T final minus what? What is the starting temperature of the calorimeter? This is 18.24. That's what the solutions manual says. I find this a little confusing because what if your solutions started with a different temperature than the calorimeter? I guess they're just saying that they've both been sitting in the lab, the calorimeter and the solutions. They've come to the temperature of the lab, and that's what you're starting at. But to me, they need to be more specific. But it does make sense that both of the T finals are going to be the same, right? That's what we just talked about in the previous problem. The idea is with these heat transfer or calorimetry problems, the substance or reaction in question comes into thermal equilibrium with the surrounding calorimeter. So the T finals are the same. And I guess in a lot of cases, the initials are the same as well because the substances in question or that are going to undergo the chemical reaction are both, and the calorimeter have been sitting in the lab, and they've come to the temperature of the lab. Okay, so now this is just an algebra problem. Solve for TF. And you get 22.5 degrees Celsius. That is the final temperature of the mixed solution and the calorimeter.